Welcome to this problem walkthrough. Today, we'll be exploring LeetCode problem number 1688, count of matches in tournament. This problem challenges us to calculate the total number of matches in a tournament where teams compete until a single winner remains. Let's dive in and break this down step by step. In this problem, we need to calculate the total number of matches played in a tournament where teams compete until only one team remains as the winner. The tournament follows specific rules based on whether the number of teams is even or odd. When the number of teams is even, each pair of teams plays a match, and half of the teams advance to the next round while the other half are eliminated. On the other hand, if the number of teams is odd, one team automatically advances to the next round without playing, and the remaining teams compete as if the number were even. By the end of the tournament, we need to return the total count of matches played to determine the winner. The input to this problem is a single integer, n, which represents the number of teams in the tournament. The value of n can range from 1 to 200. The output will be a single integer representing the total number of matches played throughout the tournament. To better understand this, let's explore some examples. In the first example, if n is 7, the tournament proceeds as follows. In the first round, there are 7 teams. Since the number is odd, one team automatically advances, and the remaining 6 teams play 3 matches. At this point, the total number of matches played is 3. Continuing from the same example, after the first round, 4 teams remain. These 4 teams play 2 matches in the second round, bringing the total number of matches to 3 plus 2 is equal to 5. In the third round, only 2 teams remain, and they play one final match to decide the winner. This brings the total number of matches to 3 plus 2 plus 1 is equal to 6. So, when n is 7, the winner is decided after 6 matches. Let's look at another example to reinforce this concept. If n is 14, the tournament starts with 14 teams. In the first round, since the number is even, all teams are paired off, and 7 matches are played, resulting in 7 teams advancing to the next round. The total matches at this stage are 7. In the second round of the same example, with 7 teams remaining, the number is odd. One team automatically advances, and the remaining 6 teams play 3 matches, bringing the total to 7 plus 3 is equal to 10. In the third round, 4 teams compete, and they play 2 matches, making the total 7 plus 3 plus 2 is equal to 12. Finally, in the fourth round, the last 2 teams play 1 match to determine the winner, bringing the total matches to 7 plus 3 plus 2 plus 1 is equal to 13. For this input, n equals 14, the winner is decided after 13 matches. Now consider the edge case where n equals 1. In this case, no matches are played since there is only one team, which is declared the winner by default. Therefore, the output is 0. There are a few key edge cases to consider for this problem. When there is only one team, no matches are played, and the result is simply 0. If the number of teams is even, the matches proceed smoothly, with half the teams eliminated in each round. However, when the number of teams is odd, one team automatically advances in each round, while the remaining teams compete as if the number were even. Finally, at the upper limit of the constraints, where n is 200, the solution must handle the calculation efficiently even with a large number of teams. These considerations ensure that our solution works correctly across all possible values of n. To solve LeetCode problem number 1688, count of matches in tournament, we need to calculate the total number of matches played in a knockout-style tournament with n teams, where teams compete until only one remains. Let's explore 2 approaches. First, the brute force simulation approach. Here, we simulate each round of the tournament, dividing teams into pairs, counting the matches, and updating the remaining number of teams until one is left. For example, if there are n teams, the number of matches in each round is n//2. Afterward, the remaining teams are computed as n equals n//2 plus n%2, where odd teams result in a bye. This approach is efficient, with a time complexity of O log n, as the number of teams is halved each round, and a space complexity of O 1. However, while straightforward, this method unnecessarily simulates the process. Next, we considered a mathematical derivation approach. Here, we recognize that every match eliminates exactly one team. To reduce n teams to 1, we need n1 eliminations, which means n1 matches. This insight allows us to directly compute the result without iterative simulation, achieving constant time and space complexity, O1. The key observation that underpins the mathematical derivation is simple yet powerful: each match corresponds to exactly one team being eliminated. This means the total number of matches required to determine the winner is exactly the number of teams minus 1. Based on this insight, we chose the mathematical derivation approach as our optimal solution. While the brute force simulation approach is intuitive and follows the tournament process step by step, it performs unnecessary computations. In contrast, the mathematical approach is faster, simpler, and more elegant. It avoids iterative calculations entirely, leveraging the elimination structure of the tournament to provide an immediate answer. Comparing the two, brute force is easier to understand for beginners and aligns closely with the problem's narrative, but it's slightly less efficient. On the other hand, the mathematical approach offers optimal time and space complexity, O1, but requires recognizing the core mathematical insight. By prioritizing efficiency and simplicity, the mathematical derivation is the most robust and scalable solution for this problem, making it the clear choice. In this problem, we're tasked with finding the total number of matches played in a knockout-style tournament wherein teams compete. The key observation here is that every match eliminates exactly one team, and the process continues until only one team remains. Instead of explicitly simulating each round, we can simplify the problem by leveraging the fact that the total number of matches required to determine a winner is always n1. This is because to reduce n teams to 1, we need to eliminate n1 teams, and each match removes exactly one team. Let's first understand the rules of the tournament. When the number of teams is even, all teams are paired, and the number of matches in the current round is simply n/2. If the number of teams is odd, one team automatically advances to the next round, and the remaining teams are paired, resulting in n1/2 matches for that round. This insight forms the basis of our approach. The most important insight is that each match reduces the total number of teams by 1. This means the total number of matches required to reduce n teams to 1 is exactly n1, since that's how many teams need to be eliminated. If we wanted to simulate this process iteratively, we could do the following: initialize a variable total_matches to 0. Then, while there are more than one team remaining, we calculate the number of matches in the current round. If n is even, the number of matches is n/2. If n is odd, we calculate n1/2 matches and account for the team that automatically advances by adding 1 to the number of advancing teams. We'd then update total_matches with the number of matches just played and update n to the number of teams advancing to the next round. However, the iterative simulation isn't necessary for solving the problem. Since the total number of matches equals the total number of eliminations, we can directly return n1 as the result. The core idea behind this problem is that every match eliminates exactly one team, and this process continues until only one team remains. Therefore, the total number of eliminations is equal to the total number of matches. This leads to the observation that to reduce n teams to 1, we need exactly n1 eliminations, which means the total number of matches is simply n1. This direct formula helps us avoid the need to simulate the tournament round by round. While we can simulate the process iteratively, it's unnecessary because the number of eliminations, and hence the total number of matches, can be calculated directly. This makes the solution both optimal and efficient. In terms of complexity, the time complexity is O1, since the result is calculated with a single subtraction, and the space complexity is also O1, because no additional data structures are needed. For this problem, no additional data structures are required. If we were to simulate the process iteratively, we'd only need a single variable, total_matches, to keep track of the count of matches. Let's also consider the edge cases. For the smallest input, when n equals 1, no matches are played, which aligns perfectly with the formula n1, giving an output of 0. For very large values of n, such as 10⁻⁹, the formula remains efficient because it avoids any iteration, making it scalable even for the largest inputs. Finally, when the number of teams is odd, the formula still holds because it directly calculates the total eliminations required to determine a winner, without needing to simulate the intermediate rounds. This makes the solution robust and applicable to all valid inputs. Let's walk through an example to solidify our understanding. Suppose the input is n equals 7. We start with 7 teams. In the first round, 3 matches are played as 6 teams are paired, and 1 team advances automatically. This leaves 4 teams. In the second round, 2 matches are played as all 4 teams are paired, leaving 2 teams. In the third and final round, 1 match is played between the remaining 2 teams, leaving a single winner. Adding up the matches, we get 3 plus 2 plus 1 is equal to 6 matches in total. Using the formula, we calculate n1 is equal to 7, 1 equals 6, which matches our result. This demonstrates that the formula n1 is not only correct but also significantly more efficient than simulating each round. The elegance of this formula lies in its simplicity, as it directly leverages the fundamental property of elimination tournaments. Iterative simulation is unnecessary unless explicitly required, making the formula the optimal choice for solving this problem. This implementation solves the problem of counting the total number of matches in a knockout tournament. The algorithm is straightforward and leverages the fact that each match eliminates exactly 1 team. Let's break it down step by step. 1. Initialization. We define the number of matches function, which takes n as the number of initial teams. We initialize a match's variable to 0 to keep track of the total matches played. 2. Loop until only 1 team remains. The while loop runs as long as there are more than 1 team, n greater than 1. This ensures we process every round of the tournament until a winner is determined. 3. Even number of teams. If the number of teams n is even, all teams can be paired. We calculate the number of matches in the current round as n//2 and add this to the matches counter. The number of teams advancing to the next round is then updated to n//2. For odd number of teams, if n is odd, 1 team advances directly to the next round without playing. The number of matches in this case is n1//2, as the remaining teams, after excluding the advancing team, can be paired. We add this count to matches and update n to n1//2 plus 1, representing the number of teams remaining after the current round. 5. Return the result. Once the loop exits, when only 1 team remains, the total number of matches is stored in matches, which we return as the final result. #### Key observations. Each match eliminates 1 team, so the total number of matches is always n1 for n starting teams. This algorithm effectively calculates this value iteratively. The algorithm handles both even and odd cases seamlessly, ensuring correctness for all inputs. ### Complexity analysis. Time complexity. The loop runs logarithmically with respect to n, as the number of teams approximately halves in each iteration. Thus, the time complexity is O log n. Space complexity. The algorithm uses only a fixed amount of extra space, making it O(1). This concise and efficient solution guarantees the correct result for any valid input size, adhering to the problem constraints. This is the Java implementation for LeetCode problem number 1688, count of matches in tournament. The logic mirrors the Python implementation, calculating the total number of matches in a knockout tournament. Key differences include explicit type declarations for variables, as required by Java, and the inclusion of the class structure. The method number of matches iteratively calculates matches and adjusts the number of teams until there is only 1 team left. To solve the problem of counting the matches in a tournament, let's start with an example where the input is n equals 7, meaning there are 7 teams initially. At the beginning, the total number of matches played, matches, is set to 0. In the first step, since the number of teams, n, is odd, we calculate the number of matches as n1//2. Substituting the values 7 to 1//2 gives us 3 matches. 1 team advances directly to the next round, so we update the total matches to 0 plus 3 equals 3 and the remaining number of teams to 7 to 1//2 plus 1, which is 4. Now, in step 2, n is even, meaning every team pairs up to play a match. The number of matches is calculated as n//2. With n equals 4, for //2 gives us 2 matches. Adding this to the total, we now have matches equals 3 plus 2 equals 5. The remaining number of teams is updated to n//2, which is 2, and we proceed to the next step. At this point, the number of teams, n, is 2, which is even. Again, we calculate the number of matches as n//2. With n equals 2, dividing by 2 gives us 1 match. Adding this to the total, we now have matches equals 5 plus 1 equals 6. The remaining number of teams is updated to n//2, which is 1. Once n becomes 1, the tournament ends because there are no more teams available to play matches. The total number of matches played in this case is 6, so the output for an input of 7 is 6. Now, let's consider another example with n equals 14. Here, the initial number of teams is 14, and the total matches starts at 0. In the first step, since n is even, every team pairs up to play a match. The number of matches is calculated as n//2. With n equals 14, dividing by 2 gives us 7 matches. We update the total matches to 0 plus 7 equals 7 and the remaining number of teams to n//2, which is 7. Moving to step 2, n is now odd, so the number of matches is calculated using n1//2. Substituting the values 7 to 1//2 gives us 3 matches. One team advances directly, and we update the total matches to 7 plus 3 equals 10. The remaining number of teams becomes 7 to 1//2 plus 1, which is 4. With 4 teams remaining, n is even. The number of matches is calculated as n//2. For n equals 4, dividing by 2 gives us 2 matches. Adding these matches to the total, we get matches equals 10 plus 2 equals 12. The number of teams is updated to n//2, which is 2. In the next step, n is still even, so we calculate the matches again as n//2. For n equals 2, dividing by 2 gives 1 match. Adding this match to the total, we now have matches equals 12 plus 1 equals 13. The number of teams is updated to n//2, which is 1. When n becomes 1, the tournament ends. The total matches played in this case are 13, so the output for an input of 14 is 13. Finally, let's look at a simple case where n equals 1. When there is only one team, the tournament ends immediately because there are no matches to play. The initial matches count starts at 0, and since no matches are played, the total remains 0. The output for an input of 1 is simply 0. The time complexity of this solution is O log n, and this is primarily due to the way the number of teams is reduced in each iteration of the loop. At each step, the number of teams approximately halves. For instance, if the number of teams is even, they get divided into pairs, and n becomes n/2. If the number of teams is odd, one team advances automatically while the rest are divided into pairs, which still reduces n to approximately half its value. This halving process continues until there is only one team left. Because the number of iterations required to reduce n to 1 corresponds to the logarithm of n with base 2, the total number of iterations is proportional to log n. Since each iteration performs a constant amount of work, such as basic arithmetic operations, the total time complexity is O log n. This explains why the solution is highly efficient for large input sizes. The space complexity of the solution is O(1), meaning it uses a constant amount of memory regardless of the input size. This is because the algorithm only relies on a few variables to keep track of the current number of teams and the total matches played. Specifically, we use variables like matches and n, and no additional data structures such as arrays or lists are required. All computations are done in place, and the memory usage does not grow as n increases. This makes the solution not only time efficient but also space efficient, as its memory footprint remains steady no matter the size of the input. When comparing this optimized approach to a potential brute force method, the difference in efficiency becomes clear. A naive solution would involve simulating each round of the tournament explicitly. This would require maintaining a list of remaining teams and iterating over all teams to form matches, which results in a time complexity of O(n). Additionally, storing and updating the list of teams would increase the space complexity to O(n). In contrast, the optimized approach avoids these inefficiencies by directly calculating the number of matches in constant time for each round and iteratively reducing the size of n. This reduces the time complexity to O log n, and the space complexity to O1, making it far more scalable and practical for larger values of n. To solidify our understanding of the time complexity, we can provide a mathematical proof. The critical insight is that the number of iterations corresponds to how many times n can be halved until it reaches 1. If we let n be reduced to 1 after k iterations, we can express this as n/2 to the power of k equals 1. Solving for k gives us k equals log_2, n, which directly shows that the number of iterations is proportional to log n. Since each iteration performs a constant amount of work, this confirms that the time complexity of the solution is O log n. This mathematical reasoning aligns with our earlier explanation and highlights the efficiency of the approach. One common mistake when solving the count of matches in tournament problem is misunderstanding the halving process. While it's true that the number of matches per round is n/2 when the number of teams is even, this doesn't hold when the number of teams is odd. In those cases, one team advances without playing a match, and failing to account for this can lead to incorrect calculations. Another issue is not including the final round in your count. This frequently happens when iterating through the solution but stopping before the very last match that determines the winner, leading to an off-by-1 error. Overcomplicating the solution is another pitfall. Some people simulate each round explicitly, reducing the number of teams iteratively, but this is unnecessary. A direct formula like n1 can solve the problem efficiently in O1 time. Additionally, arithmetic errors, particularly when handling odd numbers, can creep in. For example, confusing the floor of n/2 with a floating point division result can throw off the match count. Finally, in iterative solutions, failing to properly update the number of teams or forgetting to stop when only one team remains can result in infinite loops, which are a common bug to watch out for. Now, let's look at how this problem is commonly approached in interviews. Interviewers often use this problem to test your ability to think critically about iterative processes and identify patterns. Recognizing the n1 formula quickly demonstrates strong problem-solving skills. It's also important to be able to explain why the formula works. Each match eliminates exactly one team, so with n teams, you will need n1 eliminations to reduce the pool to just one winner. Variations of this problem might ask for the number of rounds instead of matches, or might modify the elimination rules, such as using double elimination instead of single elimination. Additionally, this problem is closely related to others that involve similar reasoning. For instance, LeetCode 231, Power of 2, tests your understanding of halving numbers. LeetCode 263, Ugly Number, requires iterative processes and divisibility checks. LeetCode 258, Add Digits, involves deriving simple formulas for repetitive processes. Lastly, LeetCode 509, Fibonacci Number, explores the trade-offs between iterative and formula-based approaches, much like this problem. There are several ways to approach solving this problem. One option is iterative simulation, where you calculate the number of matches in each round and reduce the number of teams accordingly. While this approach is easy to conceptualize, it is less efficient, with a time complexity of O(n). A faster alternative is to use the mathematical formula n1, which provides O(1) efficiency. However, this method requires a strong understanding of why the formula works, as you may need to explain it during an interview. Another approach is to solve the problem recursively, breaking it into smaller subproblems. While this method can be elegant and aligns well with divide-and-conquer strategies, it might be overkill for a problem as straightforward as this one. Each of these approaches has its trade-offs, so it's important to understand which is appropriate depending on the context or the interviewer's preferences. Great job following along. To recap, we calculated the total matches in a knockout-style tournament using a simple and efficient approach. This problem reinforces the importance of simulating processes and understanding iterative solutions. Thanks for tuning in. Be sure to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!